at section 7.2 today. Transformations of exponential functions. You've seen this stuff before because transformations was all chapter 1. We used to apply it to the trig functions. That was chapters 4 and 5. Now we're going to apply it to the exponential function. So to start out, I want to use that basic function again, and that's going to be y equals to 2 to the power of x. I'd like you to graph that out using a table of values, and once again, let's see if we can, let's see if you can put in some values here that are less than 0. How about -3, -2, and -1? We did those last time. That's 2 to the power of -3, which is 1 over 2 cubed, and I think you remember that should be 1 over 8. So since you remember, I'm just going to tell you all the other ones. Remember, 2 to the power of 0 is just 1, 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the power of 4 is 16. So as we do this, we're going to plot these points again. 2, oh, that was not good. 1 should be 2, right? 2 should be 4, 3 should be 8, 4 is now 16. We connect the dots. Whee! Okay, there's y equals to 2 to the power x. Now, remember last day we used this kind of formula quite a bit. A c to the power x. So for example, if I made like a like a number, let's say it's 3, so let me just do this. You don't need to do this in your notes, but I just wanted to show you. And the c value is still 2. We have now 3 times 2 to the power x. If I made a table of values, once again, just starting at 0, you'll notice this is 3 now instead of 1. And then this would be 6, right? 6. This would be then 2 squared is 4. 4 times 3 is 12. And notice, just like all the other graphs that we had before, in chapter 1, this 3 represents our vertical expansion by a factor of 3. Remember that kind of stuff? Well, it's the same thing here. So we're going to do all these different transformation types. I'm going to use different letters this time. I'm going to say A, and then there's the B, then there's H, and there's K. So these 4 parameters, which were talked about in chapter 1, and here's a quick summary of all those. Ain't I nice that you don't have to write these down yourself? So we've got when k is bigger than 0, of course that's, remember, outside the function, so the a and the k's are outside the function, and therefore they affect the y value, and they're normal. Okay, it's the b and the h that are affecting the x, and those are always counterintuitive of what you think they should be. So I hope this is a good review for you. I'm not going to go through this, but please read it. Because if you turn the page, our next question now is to take that original graph of, let's say, y to the power of 2x. Sorry, y equals 2 to the power of x, I should say. And I want you to identify the changes, and I want you to also map the transition of some key points to see what this new graph will look like. Okay? So, we're going to compare this. Okay? So we're going to compare to our original y equals 2 to the power x graph. So that 3 value, like I said earlier, that just means it's a vertical expansion by a factor of 3. So when you expand that, your y values stretch by a factor of 3. We also see something else. I think we see this x plus 4, and that means you're looking at something horizontally being done. X plus 4 you think go to the right, but no, it's a shift actually to the left. Remember, horizontal is always opposite of what you think. So 4 units. And then the last but not least, the minus 1, is you're just going to vertically shift. And in this case, yep, you guessed it, down 1 unit. So these are the 3 things that we're doing in example 1a. I'm going to ask you to quickly graph out y equals 2 to the power x first. And I've given you a nice table of values down here to help us out. So let me just change my window here. Let's make it a little bit smaller so you can see both pieces perhaps. That's good. So we started off with the original graph of just y equals to 2 to the power x. I'll put that in black. So 2 is 0.25, 0.5, 1, 2, 4. We've done this one so many times. Right? That doesn't look very good. Sorry. Let's try again. There we go. The 3, once again, means that all my x values stay the same, but my y values get multiplied by a factor of 3. So instead of 0.25, it's 0.75. Instead of 0.5 times 3, it's 1.5. Instead of 1, it's now 3. 2 is 6. 4 is 12. And 8 is 24. So if I were to plot these values, 2 is 0.75. Negative 1 is 1.5. 0 is 3 now. 1 is 6. 2 is 12. And, well, the rest I can't really. Okay. Now the next one we said is a horizontal shift 4 units to the left. So I'm going to take my x values and shift it 4 to the left. So 4 to the left means negative 6, negative 5, negative 4, negative 3, negative 2, how about negative 1? All in all, in these cases, my y value stays the same because all I'm doing here is showing the horizontal shift going left 4. I know I could have combined them together, but for learning's sake, we're not going to do that. So negative 6 is 0.75, negative 5 is 1.5, negative 4 is 3, negative 3 is 6. So notice the shape doesn't really change here. It's just everything got shifted to the left 4 units. And we're almost done because now the last part is to go down 1. So negative 6, 0.75 minus 1, 0.25, negative 5, 0.5, negative 4, 2, negative 3, 5, negative 2, 11, negative 1, 23. So we'll shift everything just down 1 unit. 2, 11, 3 is 5, negative 2 is 11. So yeah, everything shifted down 1 unit. Okay, and there you have it. Now, in all these cases, what do you think happens to my domain? Domain talks about all the x values, so it still seems like all x values make sense to me, and they all work, so we keep it as all real numbers. The range, however, is interesting. Remember some general characteristics of y equals 2 to the power x? We have here the range was y is greater than 0. So if we do all these things to it, if we multiply by a factor of 3, well, 0 times 3 is still 0. But we do subtract 1, so that tells us our range must be now bigger than negative 1. And remember our horizontal asymptote for the original one was y equals to 0. Well, therefore, of course, in this case, our horizontal asymptote must be equal to 1. Okay? So probably some dotted line down here. All right. That's example A. I'm going to get you to turn the page and try example B. Let's just at least go through the first part together, and then hopefully you can do the table of values, graph it out, domain and range, and the asymptote all by yourself. All right, turn the page. Okay, I'm going to try to help you with this one, at least identifying the transformations. So, oh, yeah, there's something kind of messy in the exponent. I see a negative. Oh, don't like negatives. Oh, and I see a 2 and I see a minus 6. And remember, we're always going to use that form where there's a bracket in the exponent. So remember, y equals to a, c, what was it, b, and then it's x minus h, right? And then, oops, and then plus k. So we have to factor first, okay? So factor first. Then we can see all the parts. So y equals 0.54. I'm going to factor with the negative 2. That leaves us with x plus 3 plus 2. Okay. Now we're good. So let's start. 0.5, right? The a value is 0.5. So vertical, not expansion, compression by 1/2. Okay, that 2 here in the exponent must be a horizontal, and this is, remember, opposite, so once again a compression by 1/2. We've got that negative here. Ooh, negative, hey? Negative, so some sort of reflection. In which axis? It's next to the x, so yeah, it's a reflection in the y-axis. And then we have plus 3. So that plus 3 must be moved left 3 units. And then plus 2 means go up 2 units. Wow, 5 things, okay? So I've been nice enough to give you the base function y equals 4 to the power x already. I'm going to get you to use the table of values underneath here. And let's see if you can combine all those pieces together. Okay? So let's do the expansion compression. 0.5 and the 2. So the 0.5 represents, once again, a vertical compression by 1/2. So let's compress all these by 1/2. Negative 1, negative 1/2. Compressing 0, 0, 1/2, 1. And the y coordinates are also compressed by 1/2. So 1/32, 1/8, 1/2, 2, and then 8. Okay, let's graph that first. Negative 1, 1/32, really tiny. Negative 1/2, 1/8, really tiny. Half. Half is 2. Okay, and then 1 is 8. So really, really flat. Ooh, and then becoming steep. Okay. All right, then we have that reflection. So now we'll do the reflection, which means I make my x values negative, so 1. Keep the y values the same, 1/2. 0, well, negative 0 is the same thing. Negative 1/2. Negative 1/8. 1/32. 1/2, 1/8. 0 of a half. Same thing. And then what else do we have? Oh, negative 1/2, 2. Boop. And then last one, negative 1/8. So hopefully you see that this is just a reflection of the red graph in the y-axis. Okay. And then last but not least, we're going to go left 3 units and up 2 units. So left 3, meaning all the x values go subtract 3. 2.5, negative 3, negative 3.5, negative 4, and then plus 2, so that's 2 and 1/32, 2 and 1/8, 2.5, 4, 10. Okay. So negative 2 and 2 and 1/32, so I guess that's right about there. Negative 2.5 and 2 and 1/8, a little higher. Negative 3 and 2.5, higher. Negative 3.5 and 4, I believe it was. Okay. Negative 4 and 10. So here's our graph. And this is the final one, so y equals to 0.5, 4 to the negative 2, bracket x plus 3 plus 2. Final answer. Done. And then your domain, well, once again, it's all real numbers. No change. The range is where we see something different. And if you guessed it, yes, it's bigger than 2. You're right. And your horizontal asymptote now, of course, is at 2. Good. Right, one more example in the back, or at least 2 more, and then we're done this section. All right. Ooh, yes, I love green tea. More so than coffee, even though I start drinking coffee this year. That's what happens when you got a kid who keeps you up at night. But I still like green tea, because I'm Asian. Well, I've got a cup of green tea here. It's being heated to 110 degrees Celsius, just like how I like it, and then allowed to cool in the classroom that has a temperature of 18 degrees Celsius. So notice the cup of tea will get cooler and cooler and cooler, and it will pretty much reach room temperature and stay at room temperature. Here it says the temperature Y in degrees Celsius is measured every minute as a function of time. So I'm comparing the temperature with respect to time. And it says that it's found that the temperature of the tea decreases exponentially at a rate of 10% every 2 minutes. Okay. So I want you to then use all this information and figure out the transformed exponential function in this form. Okay, we did something like this last day with those like compounding, interest, and bacteria growth questions. So here's just another situation where you see exponential growth, or in this case, decay. Since it's decreasing, it is decay, and the decay portion is that constant c. Remember, we're taking 100% as we're starting, and because you're reducing it by 10%, that just leaves us 90%, or therefore our decimal would be 0.9. So the c value is really 0.9. And because it's done at a rate of every 2 minutes, what you can see then is that we're going to raise it to the power, and that power here, well, it should be divided by 2. So that power seems to be the b value. So the b value seems to be 1/2, because we're taking that x and we're dividing it by 2. Okay? Now, also in this case, well, maybe I'll do this first. So we'll start by writing it like this. 0.9, and then it's x over 2, right? Or 1/2 x, up to you. Okay? So now we have to look at the a value, the h value, and the k value. Well, think about what this graph looks like, the green one here, okay? It's a graph, and, it's decaying. It's getting less and less and less. Well, what's it getting closer to as it moves further and further to the right? Yeah, if you thought about it, the horizontal asymptote in this case is 0, right? Y equals to 0. But wait a minute, in our question, it seems like this cup of coffee green tea decreases in temperature until what temperature? Is it 0? No, it seems like it's 18 degrees Celsius. So really, if you think about it, my horizontal asymptote needs to be shifted up here to 18. So knowing that, I think we just solved for k. So therefore, in this case, we now know that k is equal to 18, because that's the temperature that it's going to become and stay at. Okay, that's also your horizontal asymptote. Okay. Okay, so what we have now is y equals to 0.9 power x over 2 plus 18. Okay, notice there's no change in the horizontal, because I'm assuming that here we're starting at t equals to 0. So there's no like horizontal shift. I didn't say we're going to wait 5 minutes, keep it at 110, and then let it cool. Okay, nothing like that. So that starting time, or the H value of this cooling process, is really 0 degrees. Okay? So ultimately, I think now I just haven't used that 110 degree information, and I'm thinking, that probably helps me solve for A. Well, what does it mean when I say it's initially heated to 110 degrees Celsius? Well, that means at time t equals to 0, the initial temperature, I should say x, sorry, so I used x, at x equals 0, the y value equals to 110. So if I were to put in a value of a now, just like how we did this in the past in chapter 3 and all that, when we try to solve for the a value in front, we're going to put in 110. This will be a bracket 0.9 to the power of 0 over 2 plus 18. You know 0 over 2 is just 0. 0.9 to the power of 0 is just 1. So if we're solving for a, we have here 110 equals a plus 18. Just going to subtract 18 on both sides, so a equals to 92. Okay? So ultimately, all this work should get the following formula. It's y is equal to 92 bracket 0.9 to the power of x over 2 plus 18. This is the exponential equation that describes the rate of change, I guess. Not the rate of change, but the temperature of the T as it decreases exponentially over time. And to just reaffirm what we've done here, in part B, I've asked you to describe how each parameter A, B, H, and K relates to the information provided. So the A value, of course, was 92, and that really represented what? Well, if you look at how we got 92, we took 110, take away 18. So ultimately, that's just the difference between the initial temperature and the classroom air temperature. The B value, in this case, was the, I think, 1/2, right? So that represents the interval of time over which 10% decrease in temperature occurs. Or, like I said last day, this is like the interval of time or the cycle. Okay, where I should say one cycle over one cycle of the, I guess, rate change occurs. Okay, so once again, it's the interval time, or 2 minutes. In this case, it's going to be 1/2, because it's 2 minutes. We're dividing by t. That's what we did last time. Okay. And then the h value, well, in this case, there was no h value, so there really wasn't a shift in the time. So this just represents the starting time of the cooling process. And then K, the value of K, which is 18, represents the actual air temperature in the room. And ultimately, my teacup will decrease in temperature to meet the air temperature in the room. So, just a little side note, this is also your horizontal asymptote. Okay. Those of you doing calculus, you're going to see this again. Newton's law of cooling questions, separable differential equations. Oh, good stuff. Stay tuned for that. Okay, those of you doing AP calculus. Okay, example number 3 here. We'll do one last one. Half-life questions, so you'll see a lot of these as well. So I think in this case, I've got, after 8 days, this iodine-131 loses half of its original mass. And then I got a sample that starts with 250 grams. I'd like you to write an exponential equation that models this amount. M of iodine-131 remaining after D days. So don't use Y and X, use M and D. Then afterwards find domain range, all that kind of good stuff. Okay? So I think I'm going to let you try this one on your own. I'll just silently get you started by writing this down. A C, B, X minus H plus K. Okay, and let's hopefully you can use this, or even last day's equation. And last day I think I did this, y equals to a c to x over t, right? So ultimately I want you to understand that b and that dividing by t are connected together, right? So in the connection between these two equations, b is just equal to 1 over t. All right? Okay, try on your own, please. Y becomes m. The initial amount is 250. Because it's half-life, my c must be a half. B, okay, here's the tricky part. Since it's 8 days, I guess it's 1 over 8. And its x now becomes d. There is no phase shift, or not the phase shift, no horizontal shift. Don't think there's any vertical shift as well, so we can leave it like that. Or better yet, how about m equals to 250, 1/2 to the power of d over 8. That is your equation. Okay. After we found the exponential equation, what's the domain? Well, in this context, careful, in this context, since domain represents d, the d has to be greater or equal to 0. So there's your domain. Your range in this case, well, I think your range would be all values that, of course, have to be bigger than 0. Okay, so bigger than 0. This doesn't equal to 0 because that's the horizontal asymptote, remember? And I guess you're starting with 250 grams, so it can't be more than that since it's decaying. And then last but not least, your horizontal asymptote. Well, that would just be the value of m equals to 0. So notice this thing technically doesn't ever disappear, but it gets so small, so small, so small that, you know, it does pretty much disappear. All right, that's it for 7.2. So just know how to graph, know how to do all those transformations, and just a few word problems to spice it up. Done.